Assalamu alaikum. This is lecture 16 of data structures and algorithms. Today we are going to talk about stacks. We are going to use chapter 7 of book 1 for this topic. Let us see what we did in the last lecture. We were introduced to the quicksort algorithm. We traced through the quicksort algorithm and we investigated the time complexity of the algorithm in best and worst cases. First, we talk about memory requirements of quicksort. The quicksort algorithm is an in-place or in-situ algorithm. Why do I say that? It delivers the sorted sequence in the same data structure that holds the input sequence. You give it a Python list which contains all the values that need to be sorted. It sorts those values and delivers the sorted sequence in the same Python list. So that is why we call it an in-place or an in-situ algorithm. So it does not use an additional Python list to hold the sorted output. However, the algorithm uses a stack to hold upper and lower bounds of the subsequences that remain to be sorted. So we cannot say that the algorithm does not use any additional memory. It does use some additional memory, the memory that is taken up by the stack. Every time the pivot sits in its correct position, the subsequence of values lower than the pivot is stored in the stack and sorting commences in the subsequence of values greater than the pivot. The maximum number of elements pushed onto the stack is determined by the number of nodes in the longest branch of the tree formed by the algorithm. Let us look at the example through which we traced when we were understanding the quicksort algorithm. This was our input sequence. We started with 12 elements. When the first pivot found its correct position, this sequence broke off into two. One containing 4 elements, these elements had values lower than the pivot. Another containing 7 elements with values greater than the pivot. What we did was we pushed the lower valued subsequence onto the stack. And then we started running quicksort in the subsequence of 7 elements shown on the right. When the pivot found its correct position, we found that we had a subsequence of elements lower than the pivot and the number of elements here were 5. Since it was the only subsequence that broke off, we started sorting this sequence. Then this sequence broke off into two subsequences with 2 elements in the lower valued subsequence and 2 elements in the upper valued subsequence. When we were done sorting these, we went back to the subsequence of 4 elements, and after the pivot found its correct position, we were left with another subsequence of 2 elements which we sorted. And here in front of you is a tree which was formed by our tracing through the quicksort algorithm for this input. Another thing that I want you to recall is that the maximum size of the stack in this example was 3. You can go back and check. Now look at the longest branch of the tree. The longest branch of the tree is this branch. 12 to 7 to 5 to 2. This is not the only longest branch. There is another longest branch as well. 12, 7, 5 and 2 on the left now, not 2 on the right. And the maximum size of a stack is 3, and the edges in the longest branch are also 3. And this is what I want to explain to you, that the size of the stack or the number of elements on the stack is determined by the longest branch of the tree which generates for the quicksort algorithm. Obviously, every different input sequence will give rise to a different tree. Best case memory requirements of quicksort. In terms of memory usage, the best case of quicksort happens when the correct position of the pivot is in the middle of the n element sequence in every pass. In every pass, subsequences of nearly equal length break off on both sides. The resulting tree has branches of nearly equal length. For every subsequence with more than 2 elements, we push a subsequence onto the stack. In the tree of quicksort, there are n divided by 2 to the power 0 elements in level 0. There are n divided by 2 to the power 1 elements in sequences of level 1. There are n divided by 2 to the power 2 elements in sequences of level 2. Continuing this trend, let the last level be x. There are n divided by 2 to the power x minus 1 elements in sequences of level x minus 1. And there are n divided by 2 to the power x elements in sequences of level x. Since the last level is x, the second last level must be x minus 1. We know that the sequences of level x have one element each. This means that n divided by 2 to the power x is 1. From here, I can say that 2 to the power x is n, and if I take log to the base 2 on both sides, x becomes log of n. We push a subsequence on stack in all but the last 2 levels. We don't push a subsequence when we have only 2 elements, and also we do not push a subsequence when we have just 1 element. So this means that we push a subsequence on the stack from level 0 to level x minus 2. Number of levels from 0 to x minus 2 is x minus 1. So the maximum length of the stack is x minus 1 or log of n minus 1. And from here we can conclude that space complexity of the best case of quicksort is O log n. Worst case memory requirements of quicksort. In terms of memory usage, the worst case of quicksort happens when the sequence is already sorted in ascending or descending order. The correct position of the pivot is at the first or the last index of the sequence in every pass. The longest possible subsequence breaks off every time. The resulting tree has branches differing in length by only 1. For every subsequence with more than 2 elements, we push a subsequence onto the stack. We have assumed that the sequence is sorted in ascending order. This will generate the tree that you see on the right. In the tree of Quicksort, there are n-0 elements in level 0. There are n-1 elements in level 1. There are n-2 elements in level 2. Continuing this trend, there are n-2 elements in level n-2, and there is n-1 element in level n-1. The total number of levels are n from 0 to n-1. We push a subsequence on stack in all but the last 2 levels. We do not push onto the stack when we have only 2 elements, and we also don't push on the stack when we have just 1 element. So we push onto the stack from levels 0 to level n-3. Number of levels from 0 to n-3 is n-2. So the maximum length of the stack is n-2. From this we can conclude that the O notation of the space taken by worst case of Quicksort is ON. A point to note is, in the best case, since equal length subsequences are breaking off on both sides of the pivot, we get a tree with the shortest height. Hence, it uses the smallest stack. In the worst case, since subsequences are breaking off on only one side, we get a tree with the largest height. Hence, it uses the largest stack. Summing it all up, the worst case for Quicksort is when the sequence is already sorted. It is considered the worst case because only one subsequence breaks off after placing the pivot correctly on only one side of the pivot in every pass. The subsequence breaking off is only one element shorter than the previous. Time complexity of the worst case is ON squared. Space complexity of the worst case is ON. The best case for Quicksort is when two nearly equal subsequences break off after placing the pivot correctly, one on each side of the pivot in every pass. The subsequences breaking off are roughly half the length of the previous. Time complexity of the best case is O n log n. Space complexity of the best case is O log n. So how can we optimize Quicksort? If the sequence is pre-sorted, picking the first element as the pivot will always result in the worst case. We can optimize Quicksort by avoiding the worst case scenario. We desire some way of getting close to the best case scenario for Quicksort. This results in a running time that is asymptotically the same as that of the best case. This can be achieved by a strategy in which the pivot does not sit in the first or last position in any pass. Solution number 1. Randomizing the pivot index. In each pass, generate a random number between left and right, both included. Let the random number be x. Assume the element at x to be the pivot. In other words, set lock equals to x. Remember, lock was the variable which was keeping track of the position of the pivot. This ensures the same index is not used as position of the pivot every time. Running time of each pass now includes the running time of the algorithm for random number generation. Solution number 2. Median of 3. In each pass, generate 3 random numbers between left and right, both included. Let the random numbers be x, y, and z. Assume the median of the elements at indices x, y, and z to be the pivot. In other words, set lock to the index containing the median. The median is actually the middle element in a sorted list. To get the median, you will have to take the values of the elements at x, y, and z, sort them, and then the value in the middle will be the median. Since the pivot is median of 3 elements, we know that there is at least one element larger than the pivot and at least one element smaller than the pivot. And this ensures that subsequences break off on both sides of the pivot. At least in this way, the pivot will not sit in the very first or the very last position. Running time of each pass now includes the running time of the algorithm for random number generation and the time to sort the elements of indices x, y, and z. Solution number 3. Median of first, last, and middle elements. In each pass, pick elements from indices left, right, and floor of left plus right whole divided by 2. This is actually the calculation of the middle index. So what I am trying to do is pick elements from the indices left, right, and mid. Assume the median of these elements to be the pivot. In other words, set lock to the index containing the median. The median is the middle element in a sorted list. So to find the median, you will have to take values of the elements at left, right, and mid, sort them, and the middle element will be the median. Since the pivot is median of 3 elements, we know that there is at least one element larger than the pivot and at least one element smaller than the pivot. This ensures that subsequences break off on both sides of the pivot. In the least, this will ensure that the pivot never goes to sit in the very first or the very last position. Running time of each pass now includes the time to sort the first, last, and middle elements of the sequence. We are not doing any random number generation here. Some homework for you. You do not need to submit this, but this will help you practice and prepare. Number 1. Run the Quicksort algorithm for the given sequence of keys. Use solution number 3 for optimization of Quicksort. So I want you to run the Quicksort algorithm, but don't pick the first element as the pivot. Pick the pivot according to solution number 3. Homework 2 says change the Quicksort code I gave you a file, sort with stack. It contains the quicksort code. So change the code to implement solution number 1 for optimization of quicksort. Now our topic is recursion, and we will use chapter 10 of book 1 for this topic. If you're wondering why I chose this this image is a recursive image. A name for this image is fractal. It is a fractal. A fractal is generated when you use the same motif again and again. You use one motif inside another motif inside another motif. So you are using the same thing again and again. This is a computer generated fractal that you see here. And this is one of the applications of recursion. One application of stacks is the runtime stack. I am including this in the recursion part because the book talks about runtime stack in chapter 10. Transfer of control. Transfer of control means taking processor from one entity and giving it to another, or changing the value in the program counter of the machine. Each time a function is called, an activation record is automatically created in order to maintain information related to the function. One piece of information in the activation record is the return address. This is the location of the next instruction to be executed in the calling function. When the called function returns, the return address is obtained from the activation record, and execution can resume from where it left off in the calling function. The activation records also include storage space for local variables. A variable created within a function is local to that function and is called to have local scope. Local variables are created when a function begins execution and are destroyed when the function terminates. Management of activation records. An activation record is created for every function call. The system must manage the collection of activation records and remember the order in which they were created. Remembering the order of creation allows the system to return to the next statement in the calling function when a called function completes. The system stores the activation records on a runtime stack. The runtime stack is a stack hidden from the programmer and managed by the operating system. The programmer does not initialize or create the runtime stack. The programmer cannot access the runtime stack, and the programmer cannot destroy the runtime stack. The runtime stack is created, managed, and destroyed by the operating system. This is an example to show you what a runtime stack is, what activation records are, how they are managed, and what goes on behind the scenes when we are transferring control. Start from the top left. I have a function called func1. Then underneath it, I have a function called func2. Underneath that, I have a function called mainfunc. And then I have a small script with two lines. You see these on the right in red. Actually, execution starts from the first red line in which main func is called. Main func is called, so control is to be transferred to the body of main func. Before that, an activation record is pushed onto the runtime stack. Look what is written inside the activation record. Line number 2 in red. This is the return address. When main func finishes execution, this activation record is going to take me to line number 2 in red. So now that we have pushed the activation record, let's move to main func. This is the function on the left written in white at the bottom. And the first thing it does is a print statement executing main func. Then it asks the user to enter a number. Suppose that the user enters 4. It is converted to an integer and stored in M. And then the main func function calls func1 and passes M to it. Now control is to be transferred to the body of func1. Before that, an activation record is pushed in the runtime stack. Now this activation record says line 5 main func. When func1 finishes execution, I want to come back to the 5th line of main func. Having done this, let us move to the body of func1 written in black at the top on the left. The first thing func1 does is a print statement executing func1. Then it does some calculations on the argument that it was given, x. It calculates a value of y. Then there is another print statement passing x equals 4 and y equals 10 to func2. And then func1 calls func2, passes two parameters x and y. Before transferring control from func1 to func2, we push another activation record onto the stack. This activation record says when func2 is complete, I want to come back to the 6th line in func1. Now that the activation record is on the stack, we move to the body of func2 and print executing func2. Then we do some calculation on the two arguments a and b. We calculate a c and then we execute another print statement passing c equals 7 to func1. Now there is this statement return c. This statement is asking to transfer control to the calling function. Not only is it asking to transfer control, it is also asking to take C along to the calling function. But we have forgotten who called func2. How to be reminded of that? What we do is we pop from the runtime stack. And the first activation record comes out and says go to line number 6 in func1. This is what we do. Line number 6 says print back in func1. The next line in func1 says return z. Return Z to whom? Who called func1? Again we pop an activation record from the stack. This one reads, go to line 5 of main func. So we transfer control to line 5 of main func, which says do a print back in main func. Then there is another print statement. The answer is 7. And then there is a statement return. This is a simple return. It is not asking to take a value along. But return where? Who called main func? Pop from the runtime stack. Line 2, written in red. This means we have to go to the small script written in red and start execution from line number 2. We do that and done is printed. This is how activation records and the runtime stack is used to transfer control between functions. So what did we learn today? We investigated the space complexity of the algorithm for quicksort in best and worst cases. We looked at ways to optimize quicksort. Specifically, we were talking about how to avoid the worst case in quicksort. And we were introduced to the runtime stack. At the end of this lecture, I want you to read the book, do the homework that I've set you and show it to me so that I can correct it. Note your questions for the online session and email your suggestions to me if you have any. Take care. Allah Hafiz.